got another exam walkthrough. This is going to be from 2023 June, Unit 5, from Capacitor and Capacitance. We've got question number 18. So I want you to try this question out by yourself first, and then you can watch me solve it. For the marks given examiner report, you can go to the end of the video. So it says a student planned to use a capacitor in a timing circuit. The capacitor was connected in series with a resistor to determine the capacitance of the capacitor. The capacitor was charged while measuring the current I in the circuit. The following graph was plotted. And then for part A, it says the value marked on the capacitor is 22 microfarads. Show that this value is correct. The resistance of the resistor is 240 kilo ohms. So we have the graph on top of ln current against time. Now what I'm going to do firstly is I can see those points that are plotted. So I'm going to draw a line of best fit. So it's going to be something like this. So you can take your ruler and draw the line. Okay, so that's the line. Now let's try to understand what the gradient of this graph means and what the y-intercept of this graph means. So the equation that we're going to be using here would be I is equals to I naught E minus T over RC, which is the time constant. So I'm going to take ln on both sides. We get something like this. And now what we can do is we know that ln AB can also be written as ln A plus ln B. So I can write this side as ln I naught plus ln E to the power minus T over RC. Okay, so it can be written like this. Now ln E, I'm going to talk about that in a bit, but you can move this to the front, right? So if you have ln A to the power x, you can also write it as x ln A. Okay, so that's what we're going to apply here. This is the log rule, and we'd get something like this. And then ln E is going to cancel out because ln E is equals to 1. Okay, and then we're going to get ln I is equals to minus T. You can write it like this, plus ln I naught. Okay, so I've written the T and minus 1 over RC separately. Now what we can do is we can apply the linear law. So y is equals to mx plus c. So on the y-axis we have ln I. On the x-axis we have time. The gradient is equals to minus 1 over RC. And the y-intercept is ln I naught. Okay, where I naught is the initial current. So basically we're going to be using this relation over here to answer this question. We want to find out the capacitance. So I can write this as C is equals to minus 1 over the resistance of the circuit times the gradient. And then I'll compare that capacitance value to the value they've given me in the question. So here I have taken 2 points on the graph. So minus 9.4 and 1. And then we've also taken minus 11.3 here and then 11 here. And we can write it down like this. 1 minus 9.4 and then 11 minus 11.30. So these are the 2 points we have taken. This is the x, this is the y. Okay, so that's clear. Now what we can do is we can find the gradient. So I've plugged in the values of both the points, and now I'm going to get the value of the gradient by plugging in this into my calculator. And here's the value of the gradient. It's going to be minus 0.19 per second. Okay, because again the ln values have no unit, they're unitless, and time is going to be here. So it's going to be second down, so it's going to be minus 1. Okay, now what we can do is we can plug the values into this formula. Minus 1 over the value of the resistance was 240 times 10 to the raised power of 3, and then minus 0.1. That's going to give me 2.91, and let's write 3 here as well. 2.913 times 10 to the raised power of minus 5 farads. I'm going to divide that by 1 times 10 to the raised power of minus 6 to convert it to microfarads. And that's going to give me 21.9 microfarads, which is approximately 22 microfarads. Okay, so that's the answer. So the value is correct. Okay. Right. So that's the answer to part A. Now let's look at part B. The capacitor was used in a circuit to time a collision between two identical metal spheres. These spheres were suspended from wires. The wires were connected to the circuit as shown. When the wires hang vertically, the spheres are in contact and the discharging circuit is complete. The switch was closed to charge the capacitor. The switch was then opened and the sphere A was released. The sphere A collided with sphere B. While the spheres were in contact, the capacitor partially discharged. Sphere B moved to the right. The maximum height h of the sphere above its starting position was measured, enough to calculate the maximum speed of sphere B after the collision. Okay, it's a lot of information to process, but basically what's going on here is that if you see here, we have the circuit with the capacitor, and when you close X, the switch, when you close it, the capacitor is going to charge. And then when you open the switch here, the capacitor is supposed to discharge, but it won't discharge because this other circuit is not complete, because the A and B are not, they're not together right now. They're not in contact. So when A and B come into contact, then the capacitor has a way to discharge through the resistor. Okay, so right now, what we do is we take this A. Okay, so first of all, the question says that the capacitor is charged. Okay, and then we take the A, the sphere A, and then we lift it up, and we give it energy. Okay, and when we lift it up, we give it its gravitational potential energy increases, and then when we release it, the sphere A's gravitational potential energy converts into its kinetic energy, and then it comes into contact with sphere B and gives and does work on sphere B, and sphere B gains kinetic energy, and then it moves up and loses the kinetic energy. That kinetic energy converts to the gravitational potential energy. Okay, so while they're in contact with each other, the capacitor gets a chance to discharge for some time, and yeah, so that's what's kind of going on here. Okay, so we have to calculate the maximum speed of sphere B after the collision. Now, what we can use here, we can say that the kinetic energy is lost, and that's going to be equal to the gain in gravitational potential energy. It's going to have the maximum kinetic energy here, and then as the sphere goes up, the kinetic energy decreases as the sphere does work against gravity, and the gravitational potential energy increases. At the top, your velocity is going to be 0, kinetic energy is equals to 0, and GPE is equals to max. Okay. Now we can say that half mv max square is equals to mgh max. The m cancels out. We get v max is equals to square root 2 gh max. Okay. Now we don't need the mass of the sphere even. Okay, what we can do is 2 times 9.81 times 1.1 times 10 to the raised power of minus 2, converting it from centimeters to meters. And that's going to get us 0.464 meters per second. Okay, you can write it as 0.46 meter per second. Okay, so now for part BII, it says calculate the time for which the spheres were in contact. And basically when the spheres are in contact, the capacitor will discharge. Okay, and what happens is the capacitor before the collision has this much potential difference, and after the A and B come into contact, the capacitor discharges, and then when A and B lose contact, the capacitor will stop discharging, and we end up with the capacitor having a potential difference of 5.43 volts. Okay, so the time taken for the capacitor to go from 1.8 volts, the potential difference across the capacitor to go from 6.18 volts to 5.43 volts. The time taken for this to occur is the same as the time for which these spheres were in contact. I hope that makes sense. The time taken for the potential difference across the capacitor to go from 6.18 volts to 5.43 volts is equal to the time taken for the spheres to be in contact. Okay? What we have to do here is we have to use this equation. V is equals to V naught E minus T over RC, because the capacitor is discharging. And this time here is what we need to find out. This time value is equals to the time they're asking for. Okay? This is the time value that we need. Okay, so now it's pretty easy. We just have to plug in the values here. So I'm gonna have here 5.43 is equals to 6.18 E minus T over RC, 22 times 10 to the power of minus 6 times 49. And that's going to give me, after plugging in the values, 1.39 times 10 to the power of minus 4 seconds. Now we're at the last part of the question, which says the student stated that the average force acting on sphere B cannot be more than the weight of sphere A. Deduce whether this statement is correct. Mass of each sphere is 28 grams. So we have to find the average force exerted on sphere B by sphere A. And we also have to find the weight of sphere A. After we find both of these, we're going to compare the values and say whether the statement is correct or not. Now the easier one here to find is weight of sphere A, which is the mass of sphere A times the acceleration due to gravity. That's going to be 28 times 10 to the power of minus 3 times 9.81. And that's going to give me 0.275 newtons. Now we're going to find the average force exerted on sphere B by sphere A. That's going to be equals to mass of sphere B times the acceleration of sphere B. And we can say mv minus u divided by t, where t is the time of contact. Okay? So here v is going to be the final velocity, u is going to be the initial velocity, and t will be the time of contact between A and B, because this force is the force that A exerts on B while they're in contact. So sphere B has an initial velocity of 0. When sphere A comes into contact with sphere B and exerts a force on sphere B accelerates and its velocity increases until the point where they're about to lose contact. That's when the sphere B has a final velocity v. So we can then further simplify this formula by mv over t. Now what we can do is, we already know the velocity. We got that from the first part of the question. The time we got from the previous part of the question, and we just have to plug in the values. So we're gonna have the mass, the maximum velocity or the final velocity we got from part A, and then we also got the time of contact from previous part by solving, and all of this ends up giving us a value of 92.66 newtons. We can say 93 newtons. Now we can clearly see that 93 newtons is going to be greater than 0.275 newtons, and that clearly contradicts what the student says there. It says that the average force on acting on sphere B cannot be more than the weight of sphere A. So the statement is not correct. Remember to write your comparison and your final conclusion. That's going to get you the marks. Otherwise, you might not be awarded a mark by the examiner. Okay, so that was the answer to this question.